mapping a figure to itself is just a fancy way of saying, I want to rotate this thing, I want to reflect it, I want to translate it, and I want it to look exactly the same in the exact same spot. If I translate it, you know, it would look the same, but it's probably not going to be in the same spot. So I'm going to be dealing mostly with reflections and rotations in this case. So with this one, I have a rectangle, and it seems to be, you know, centered kind of at 0, 0. If I reflect this thing across the y-axis, it would look exactly the same, and it'd be in the same spot. So I would say reflect over y-axis. That's one way that it would map to itself. Another way that I could map it to itself would be to reflect across the x-axis. Reflect over x-axis. That's another way. And I think that's it for that one. Let's slide down and look at this one. Let's try to map this rectangle to itself. This one isn't going to be on an axis. You know, if I were to reflect it on the y-axis, the rectangle would be over here. And it would look the same, but it wouldn't be in the same spot. I could reflect this thing over this line right here, and that line is reflect over x equals 2. I could also reflect it over this line, and it would look exactly the same and be in the same spot. That would be reflect over y equals 4. Okay? And I guess that I could rotate, if I'm looking to see if I could rotate that anywhere, you know, technically there's a center. If a rectangle has a center, there'd be a center of that rectangle right there. And if I rotated it 90 degrees, it wouldn't be short and fat, it would be tall and skinny, so I couldn't rotate it 90 degrees about that point. But if I rotated it 180, it would be in the same spot and it would look exactly the same. So another one would be rotate 180 degrees, and when you do 180, it doesn't matter if it's clockwise or counterclockwise, but 180 degrees about the point 2, 4. All right, let's look over here. We got a parallelogram right here. I don't know that I can reflect it anywhere. If I cut it in half, you know, and I reflect it, it's not going to look exactly the same. I don't even know if a diagonal line would do the same either, because this point would be over here, and that's not on there. But can I rotate it? You know, I don't know that a parallelogram has a center, but if it did, we would call it right there. And if I rotated it about that point, 90 degrees, it would be standing up tall, and then 180 degrees, it would be the same as it is right now. So rotate 180 degrees about, and that point is -2, 4. Okay, let's look at this one. I can reflect this one. Let's just write the word reflect right here. I could reflect it over this line, the x-axis, and I could reflect it over, is that x equals -2? Both of those would map it to itself. And I could rotate it, just like the parallelogram and the rectangle beforehand. I could rotate it about this point 180 degrees. So rotate about -2, 0, 180 degrees. I could do 360, and we normally say that 360 is given. We don't really bother writing it, but we could say 180 and 360, and then 540, 720, so on and so forth, and I'm just adding 180 each time. The last style of mapping it to itself is going to be right here, and we have a regular pentagon. And the question says, what types of rotations would map the pentagon to itself? So we're not really worried about reflections here, but rotations. And you know, if I turned it 90 degrees, this one would be over here. It wouldn't be in the same spot. So I can't do it 90 or 180, any of that kind of stuff just yet. But what I'm going to do is, I have 5 sides, and so I know that if I rotated it that angle right there, that it would be in the same spot, because that angle is the same as this angle, is the same as this angle, and it's the same as that angle. So I could say 360 divided by 5, and that's 72 degrees. So every time I rotate this thing 72 degrees about the origin, so I'm going to say rotate 72 degrees counterclockwise about the origin. It'll be in the same spot. You can even draw your L there.